So hi, my name is Zafiris Babos, and I am a senior Microsoft student partner. I am from Greece, and I'm studying computer engineering in Aristotle University of Thessaloniki. I am here with Stergios, who is also an MSP here in Greece.
Hello guys.
And today we will present to you a project we did together in our machine learning class, how to recognize software engineers from open source repositories on GitHub. Let me check the resolution. Sorry. Okay, so let's begin the presentation. First of all, in the software engineering world and in every case in the real world, when you have a project, you have to um, to implement some techniques in order to execute the project. So the most used technique nowadays for big projects is the Agile technique, the Agile methodology. And for the software engineering part, the Agile methodology means the DevOps method, which means that we have the developers, the operations, and someone who doing both. The developers are building the product, they're coding, the DevOps, they're planning and release everything, and the operations, they deploy the project on to production, they monitor, and they make questions and everything that the developers need to know from the client side, like they know it from the operations team. So what we'll do today is to try to recognize software engineer roles in GitHub repositories that we said. The GitHub is a platform which is used for software engineering projects. Every day, millions of people are uploading code in the GitHub platform, and as we can see here, that's a one-day representation of what a GitHub's repository requests are and how often people upload to code to repositories. So with the help of GitHub's API, we managed to collect some data points from open source projects, and that data consists of four main parameters: quality metrics, commit metrics, issues metrics, and activity metrics. And as you can see, we have how many lines are changed in the projects, how many violations in code we had. We have issues related metrics, how many issues closed or how many issues opened. And I hope everyone can understand what I'm talking about and what a GitHub repository is and what all these metrics are. I am thinking that most of the people are watching right now, they are software engineers on part, but we will try to keep the print as simple and as naive as we can, so even if people don't really understand what we're talking about, they could actually follow us. So for the first part of our project, we had to collect the whole data. We, as I said, we used the GitHub's API, and with the search of with the help of Elasticsearch, someone in our university built a very good data set, and he delivered it to us in order to work on our project. So once we had the data set, the first thing we did was look at it and make some pre-processing on this data. And the pre-processing we did was included 4 steps. One was missing values elimination. The second step was to exclude all of one-day developers. The second step was to exclude all the short-time contributors in the GitHub repositories, and then to normalize the data. And as we speak for that, we can go and see how we did it. So we will start coding and and present to you what I'm talking about. The whole presentation will be in R. So if you have any questions on R, or if you're familiar, I think it's really easy to understand and readable language, but we will see. So first, we're importing libraries that we are going to use, like cluster libraries. The whole problem that we're going to solve is a clustering problem. We're trying to specify some specific clusters on our dataset, so we can classify every cluster on on one of the roles that we already mentioned: developer, ops, or DevOps. So first thing is to import the dataset, and we just implement the dataset. Then we are going to transform the dataset to a data frame, and then as you can see here, we have a lot of metrics, and sorry for my tab bar, it's okay, it can stay there. So for the role classification, from all these data columns, for all these metrics, we are going to use for the issues participated, the issues opened, and issues closed, and commits authored. So we will run each one of these commands, and we are going to plot the data in order for you to see what we are having. We have so as you can see, we have the metrics I just said, and we have data points really close to the point 0, because most of the contributors in our data set was like a short time contributors, and that's why we pre-processing the data with these exact steps. So the first step, as we said, is to eliminate the missing values, and after that we are going to exclude all the one-day developers by eliminate our data set to take just a part of our data set, using the activity period in days to be less than 1. And the activity period in days, we can see here, it's a metric of the activity and the activity period in days. So yes, and in 1 second, not 1 second, in the next 10 minutes, I will present to you how you can implement some of our code in R, how you can actually execute one of our algorithms into the Azure Machine Learning Studio. So we will present the whole data set there, and you can see the whole table of our data set. So for the third part of our data pre-processing, we are going to order all the data sets based on the activity period in days, and we are going to exclude 10%, 5%, sorry, of the engineers who were participated to the GitHub repositories less than the others. So we have the data 3, and now we are going to normalize the last data set we have. And let's plot. And it's, as you can see, we have now a new data set that is from 0 to 1 as we just normalized it. And we don't have some of the data points that were close to 0. So now we can go back to our presentation and we can see the algorithms that we are going to perform in order to classify our engineers. They are 3 algorithms. All of them are clustering algorithms and they could be dbScan, k-means, and hierarchical clustering. Again, I don't know how many of you are familiar with these algorithms, but we are going to explain what these algorithms specifically do. So don't worry about that. You just need to understand a little bit of maths and you'll be okay. And of course, I know that I'm copy pasting a lot of code now and I'm executing everything like really fast, but we are going to upload everything on GitHub so you can take a look at this code at your own time as much as you want. So let's start with the first algorithm, is the dbScan algorithm, and now Stergios is going to explain to you how the dbScan is working.
So we are going to talk about the dbScan. It is an algorithm, which is a density-based clustering. In this algorithm, we have 3 categories of points, as we can see in the image. The first category is noise points. Those points have in their neighborhood at least 4 points in our example, or as many as we would like in another example. That neighborhood is defined from the EPS, which as we can see is 1. The second category is border points, and those are the ones that they are right at the border of a core point and are not core points themselves. Oh, I'm sorry. Noise points are not the first category. The first category are core points. Every other point is categorized as a noise point.
Okay, I don't know how many of you understood, but it's a complicated concept. It's of course you have to study a lot of it to understand everything, but we will implement the dbScan now on R, and you'll see how easy is to implement this and understand what EPS is and what mean points is and everything. So yeah, the main thing with dbScan is that it's very good when the data set has similar densities on space. So as you can see, our data set is has it's gathered just in one area around the zero point. So dbScan can't actually cluster our dataset, but it can be used to manipulate our dataset and exclude all the noisy points. And that's what we are going to do now with R. Again, I'm going to copy paste the code and include the library, initialize the model, and as Stergios said, the EPS is the radial of the cycle here of every point, and it has to have 4 points in this cycle in order to be a core point. And when something is not a core point, is a noise point. So we define the radial of the cycle of each point to be 0.01 as we just normalize the data, and each neighborhood has to include 4 points in it to not be a noise. So we can plot now what we have, and as you can see, all the noisy points, all the outliers are gone, because we can plot again the normalized to see the difference. As you can see, we have points in 0.8 that it's clearly, there is clearly a difference. Where is my mouse? I can't see my mouse. It's okay. So we have points at 0.8 that it's clearly far away from all the other points. So a cycle of radial 0.01 doesn't include any points. So that's a noise point, and we can see that very, very, very clearly. If I can see my mouse, everything is okay. Okay. So here is the point I was talking about. You couldn't mouse before, but now you can. So let's continue. So what we are going to do now is plot again the clusters.
Finds the closest centroid and adds it to that cluster. After all points belong to some clusters, we renew the centroids, and the algorithm goes on until it finalizes those centroids. As we can see, the initial centroids plays a very significant role, because as we can see in this image, those centroids are correctly initialized and form the groups that we want them to form. Although in the second part of the image, the centroids, as we can see, are not initialized correctly, and they cannot form and they cannot form the groups that we want them to form. So the first initialization is very, very important.
Yeah, and to define if the first initialization was good or not, we have to have some metrics, and the basic metrics that, like the core, the most common used metrics to recognize if the algorithm was the algorithm's output was good or not, is cohesion, which measures how closely related are the points in a cluster, inside the cluster, and separation, which measures how separated from each other are the points from different clusters. And what actually combines these two metrics is silhouette, which take each individual point and from the cluster and from the other clusters and make a holistic metric. So the next image is these metrics, but we're going to produce now these metrics with the R code that we are going to not write, copy paste, but still we are going to explain everything. So wait for it. So yes, first of all, we have to initialize all the arrays that we are going to use. And as you can see, is mean silhouette arrays, cohesion, separation, and we are going to find all these metrics for all our three main datasets: the original one, the normalized one, and the no irregulars one. The original one is a dataset that includes all the data with the one-day developers, with the short-term, the short contribution developers, yes. And the normalized one is the one that you showed and you saw before, and the no irregulars are the result of the DB scan. And now we are, as Stergios said, the most serious thing in k-means is the centroids and how we initialize and how many of the centroids are we initializing. And in order to find the best number of centroids that we are going to use for our clustering, we have to run a for loop and try again. I lost my mouse. I don't know why this is happening. Wait a moment. Okay. So first we initialize the model again, k-means, which is included in these libraries that we imported very first thing that we did in the script. So we initialize the model for the original data set. We say the centers are k, which at our example is from 2 to 14. And then we find the cohesion. We include the cohesion in an array in order to represent it later. We find the separation, and then we find the silhouette. Again, the whole code will be uploaded on GitHub in order for you to study it at your time. And then in the loop, we implement these metrics for all three of our data sets: no irregular, normalized, and original. And let's run it. Oops. Okay, and now let's plot the silhouette for the no irregulars. Wait for it. Okay, let's try to... Okay, so now we can see the mean silhouette for all the data sets, and as you can see, the best, like the most efficient data set is the original one, which is actually an illusion. It's a fake result, because what happened there was that in the metric silhouette, the silhouette metric counts the distance between all the points of our data set, and at the original data set we have all the engineers that were working under one day, and all these points are really close to each other. So the mean silhouette was confused and count these little, like this very strict connection between points, and determine this dataset as the best one, which is of course not the case for our project, because we know that if someone just coded for one day, he's not a good engineer, he's not even an engineer. So we can understand, like we can eliminate now the original dataset, even if we can see that our metric is the best one for the original, but still we will eliminate it, because everything you do in data science, it's actually logic. You can run everything, you can take results from maths, but the whole point is to understand what you are seeing and try to make a conclusion of all the results of the algorithms. So we are going to use as our main data set the normalized one, as we can see that the silhouette is is better than the no irregulars one. And let's now plot the cohesion as well to see. Okay, and now you can see that for the cohesion, because, and actually we have it here, so here we have the cohesion for the two data sets, the normalized and the no irregular ones that are normalized. So all the distances between the points are from 0 to 1. And here you see the cohesion of the original data, who is the scale of the y-axis is way far from the other two data sets, and that's why and that's because the data points are very far from each other when you don't normalize the data. Okay, the separation again, but we have already seen the, no, we haven't seen the separation, so we can show you now the separation. It's just the opposite of the cohesion. It's how far the the points are from each other. And what we are trying to find here is how many clusters are we going to use in order to implement this algorithm. So the for loop that we run from 2 to 14, 2 to 14 was the number of clusters to get the metrics of and decide which number of clusters is the best one for our case. Of course, if you have a small number of clusters, you can see the silhouette is really, really high, but we can't actually choose a small number of clusters because what we want to do is separate our data set with some mathematical distances in our data points. So we need to have as many number of clusters as we can with as high a silhouette value as we can. So in our case, we use the elbow method, and we can see that the sixth point is high valued enough in the silhouette and high number enough in the number of clusters. So what we are going to do is use specifically the 6 centers, plot the cohesion, the separation, and the silhouette. And now you can see how well, it's not actually very well, but you can see how the cluster, how the k-means algorithm separated our data to 6 clusters. And you can see with these box plots how many data points we have on each cluster. Okay, and we have it here all together. So the first cluster has engineers who don't have a lot of issues closed, they don't have a lot of commits authored, they don't have a lot of issues participated, and they don't have a lot of issues closed, issues opened. And that got us into thinking, like, what kind of engineer is this one? And that's why we said that we are going to implement the hierarchical clustering as well to get results from there too. But before we do the hierarchical clustering with you, I want to show you how easy it is to build a k-means algorithm. A k-means clustering with Azure Machine Learning Studio. So what we are going to do now is start a blank experiment. Okay. Wait for it. I think Microsoft has to implement some music sounds here.
Yeah.
As long as you wait. Okay, come on. Come on. No. Okay. It will ask us to log in again. No.
It won't.
Okay, sorry for that. And actually, we don't have that much time. Come on, Azure, come on. Okay, so our blank experiment is ready to be filled. And what we are going to do is use our CSV that we uploaded in our datasets in Azure Machine Learning Studio. Tomorrow it's going to be a presentation about all the things you can do with Machine Learning Studio on Azure. But now we will have a very quick example of what you can do. So first of all, you implement the dataset, and as I promised, now we can see the whole table of our dataset, and you can see the repository name, the contributor login, the average issues commented length, the length. You can see the issues closed that we just used to cluster the dataset, the issues opened, issues participated, the issues closed per day, early addition, all the metrics I showed you in the PowerPoint. So next thing, we are going to pre-process the data, and how are we going to do it is by splitting the data, and splitting the data based on relative expression, and that relative expression would be the column name to be greater than 3. I don't think so, but it can be the activity period in days to be less than or equal to 1. And that's exactly the code we wrote in R to do it, but here it's way simpler. But when you can't find, or Azure Machine Learning Studio doesn't actually have something for you, you can always write the script, and you can have it on R or in Python. So here, the split data here at the point 1, we have all the data points that are the activity period in days are less than or equal than 1, and here we have all the other points. So what we are going to do is take this data set and implement it, like give it as an input to the R script, and here we can code in R a very familiar and very user-friendly interface by Azure. Not friendly at all, but you can use it to write any R or Python code you want. And what we are doing is getting the input data set which we just inputted from the output of split data, and pass it in a variable dataset 1. We are going to create a data 2, which is actually the same code that we wrote here, data 2, in order to order the data with the activity period in days variable, and then exclude 5% of our data sets, the short-term contributors. So it's exactly the same code. We are getting only the 4 columns, and we are going to plot the data as well and make it as an output. So here everything is fine. We can run it in order to see what we will have. Again, we need music, but it's okay. It could be like a train sound, something to be like the sound of someone who's working. Okay, so here we can visualize the data. Come on, okay. And we can see that in the average, wait, I have to find it, in the activity period in days, we don't have any engineer who actually contributed only 1 or 0 days. And here we can see our data plotted, the second output of the R script. So exactly the same data we printed in the R Studio. it's here as well. And here, now it's all the magic, because Azure Machine Learning Studio has built-in algorithms, machine learning algorithms, and they have k-means clustering. Oh yeah. And let's see the parameters. Like, we can see the parameters can range from 2 to 900. We just did 2 to 14 to to determine how many clusters do we want, but as we already did it, we can just put 6 centroids. We can use the k-means plus, which is a, like, Microsoft has a lot of k-means relative methodologies here and algorithms, but we're just gonna use the default one. We're gonna use the Euclidean method of distance countance, and we're gonna have 100 iterations in order the centroids to be magnetized at the points that they have to be. Next step for our machine learning project is to train the clustering algorithm. So training our clustering model, we're going to import the k-means cluster, import the data set, and here we have to define on which columns of the dataset we want to implement the k-means, but we already excluded all the other columns we had, so we're going to use all of ours. Okay, perfect. Next step is assign. Like, I'm searching here in order to be very quick for you, but you can find everything like in categories here in the project manager panel. So after the training of the model, I want to take all the clusters and assign every data point to a cluster that was found from the training. And where I'm supposed to find something like this is at the data transform, manipulation, split data, scale, assign. I'm searching for assign. Okay, I'll just search it. Oops. Okay, assign data to clusters. So what we have, again, we are going to give it, and you can see that if you are just click to an output of one block, it tells you where it should go. It doesn't let me connect it with any other point except the right one. So what we have here, the clusters that we just trained and the data points. So if we run it, you will see all the clusters that we created with Azure Machine Learning Studio. Come on. Okay, perfect. Let's see the output of assigned data to clusters. Perfect. We have 6 clusters. We have the data points like the outliers, and we can see that there are 3 clusters, one into the other, and that's because Azure, when it tries to visualize the clusters, it uses the PCA method. If you don't know what PCA means, principal component analysis, yeah, principal component analysis, you have to search it on your own because it's again a complex mathematic metric method to manipulate data that is really hard to explain right now. But if you go to more help in this blog from Microsoft's documentation, you can find everything you want. I'll go back and I will continue our project until this page loads. And next step, I want to convert our clusters to a data set in order to see all and run it again in order to see which points are in which cluster. And now that loads that, and here it says that this module returns the data that contains the probable assignments for each new data point. It also creates a PCA graph, and you have to search it on your own what PCA is. And here, final step for this quick machine learning, Azure Machine Learning Studio tutorial, we can see each one of our data points in which one of, like the first one, we have two issues. We have issues opened, issues commits, and this assigned to the fifth cluster. And the distances, you can see the actual distances for each cluster. And as you can see, for the fifth cluster, it's the smallest one, so it matches to the fifth cluster. Okay, that was it for the Azure Machine Learning Studio, and now back to the hardcore coding with R. Not that hardcore, it's copy-paste, but we are cool anyway. So the next algorithm we are going to use is hierarchical. And hierarchical clustering, again, Stergios is gonna try to explain to you what is happening with hierarchical clustering.
So, in hierarchical clustering, we are going to use the bottom-up version of the algorithm, where we first, each point is a cluster, and then we combine those points in order to form bigger clusters, as we can see in the diagram. This method requires first to define the distance based in which clusters are going to be combined. Here we choose the Euclidean distance because as we are going to see in our example, it produces the better result. Although we can also use some other distances like Manhattan, but in our example it wouldn't produce just as good results as the Euclidean. So now we are going to code the hierarchical clustering and see those diagrams that you see right now.
Yeah, we are going to produce the same diagrams that we produced for the k-means, the cohesion, and the actual metric that it's most important because it combines both cohesion and separation and silhouette. So so as Stergios just said, we are going to use the Euclidean distance for this problem as Azure did for its own here in the k-means parameters. And I will just again include the whole code here. Okay, I think there is a problem. Can you hear us? Sorry for that delay. One second, please. Live streams are always hard. Okay, we can continue, I think. Okay, perfect. So what we have here, wait a second, I lost it. We just, okay, we have k-means. Okay. So we are going to implement the hierarchical clustering now. So hierarchical clustering, the complete method, we are counting the Euclidean distance, which is really easy to do so with R. You just call the distance function and you specify your data set and just use method Euclidean. And again, for the hierarchical complete, we are using the hierarchical lust, which is again one of the functions in I think is in library cluster, but I'm not sure. Actually, I'm pretty sure.
Yeah, it is. It is right there.
Yeah, and we do it. We count. We count the Euclidean distance for both our data sets that we're interested in. We just stopped being interested in the original data set, so we're not gonna work with the original one. And now what the difficult part of our code was, and what we spent like maybe 3 hours trying to figure out, is why at the hierarchical clustering they didn't include a method for cohesion, separation and silhouette, as they did very easily with these taught with ins, like the total distance within the cluster for cohesion in k-means, and they didn't include any method to be able to take the cohesion and separation from these hierarchical clustering functions. So we had to do it on our own. The code here, like, I don't find it meaningful to explain to you what each of these lines do, but again, we're going to upload everything on the GitHub, so we have all very well documented it and very well commented it, so you can find everything. So distances, RUP, and UWSS. WSS is actually the cohesion, and TSS is the silhouette. Yes.
It stands for total.
Yeah, it stands for total. And now that you started saying what it stands for, what is as an S.
Oh god.
You don't make these mistakes, man. You don't make them. So we initialize again all the arrays we need for the metrics that we need for every data set, and again we're going to use a for loop from 2 to 20 to say in what level, how deep we are going to cut our tree in the cluster. As you can see here in the presentation, when you're doing a hierarchical clustering, you have a dendrogram, and you have to decide how deep you're going to cut this tree and how many clusters you're going to take again. So running this for loop, we are having something like this. We don't have anything because we have an error message, and the error message is normalized complete didn't. Okay, I just didn't run the whole code. Okay, now we can plot it. It's pretty bad, I think. No, just the no regular ones. They have pretty good, pretty bad silhouette for each of their points. No, the cohesion is this one. Oh my god, I'm so sorry. So we can see here the silhouettes, and as you can see, again they normalize the Euclidean one as it was for the k-means. Like in k-means, we saw that the normalized dataset had the best and not fake silhouette. So it's the same thing with the hierarchical clustering. We can see this diagram here in a bigger picture. So what we can see here and what we will use for our project is that with hierarchical clustering, we can take 5, 6, 7 clusters. It's more than 6 that we took from k-means, and with a silhouette value of 0.9. And as you can see, at k-means, the silhouette value at 6 clusters, it was 0.8. So the best case scenario, like the best algorithm to use for these data sets to make as many clusters as you can, is a hierarchical clustering, and that's what we did. So we took 7 clusters. So we cutted the tree of the normalized data set of the Euclidean distance of the HC complete algorithm, and we cut it with 7 clusters, and we plotted, and that's how it separated our data in clusters, but that doesn't tell us anything. So we are going to plot the box plots, blah blah blah, and we have it all together here. So here we can see, if you remember from the k-means, the first cluster had everything very, very low, and we couldn't make any logical explanation out of it. But here we have the first cluster to have low issues participated, low issues opened, low issues opened, and many, many commits authored. And that's for sure, I think it was a developer. Oh, I had a whole icon, like a slide. I had a whole slide to explain why we choose the hierarchical, but I explained it on my own. It's okay. So for the role classification, we choose again the. What do we have this here? Okay. We have the hierarchical clustering in normalized dataset, and we have 7 clusters. You can see the data points that they are included in every cluster, and here is a table that says that the first cluster has low, 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 high, so it's probably a developer. The second one is low, 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 just as the case was with the k-means, so we just took it as an undecided. We have a mid, low, low, high for the third cluster, so again it's dev, let's see, and DevOps, which has everything high. As we said, DevOps makes a little bit of everything, so it's logical to have everything high. And for the ops, we have a lot of issues participated, but every other, we don't have issues open, we don't have comments authored. So yeah. But what we actually saw in our data set here at this second cluster, we had most of our points in the second cluster, and the second cluster was undecided, so most of our data wasn't classified yet. So what we could do, we just clustered again, we just implement hierarchical clustering again, deeper now, using only the data from cluster 2. And let's see how we did it. We called it a deep role classification of part of the project. Okay, a deep role classification. How cool is the deep role? It sounds like deep learning, but it's not. So we took every point of the second cluster, and we made a second dataset. And look how many points did we have at the second cluster. So again, we count the distance between these, the Euclidean distance between these points. We implement the hierarchical cluster model, and we run a for loop for 2 to 14 clusters. And here the cohesion, here the separation, here the silhouette. And as you can see, again, we have very, very, very high values for the silhouette at the very first three clusters, but we can't just use 3 clusters. So what we did was to take the elbow technique and use 7 clusters, which is the highest value one with the highest number of clusters that we can take. And that's how it went to cluster our data again. And here is again the data, the box plots, and here we have them all together. And again, for these box plots, we classified once again, and we just found once again that at the second cluster it was undecided. So what we could do was to take the second cluster again and do all the process again, but we didn't do it because what's the point? We had enough data to work and to separate, to classify our developers, our software engineers, to developers, ops and DevOps. So we took what we had and we tried to evaluate their work based on the other metrics that we had. So what our next step is to take only the developers, like only one role of the roles classification that we just did. Like we took the from the first clustering, we took the first cluster, the third cluster, yeah, just the first and the third, and from the deeper one we took the first, just the first. Yeah. And we made a new data set which is only the developers. Okay, so the roles evaluation, and let's script once again. Okay, let's create a new script, and now let's do kind of the same work, but now like I'm going to run everything again, include the dataset, pre-processing, but at the pre-process now we don't only have the issues participated, issues opened, issues closed, and commits authored, but we also have violations added, violations eliminated, average time to close an issue, and issues closed per day. And that's how to define how well a developer did his job. Okay, so with these 4 metrics we classified our developers, and with these other 1, 2, 3, 4, 4, with these other 4 we are going to classify, to evaluate his job. Okay, perfect. Stergios is looking at me like I'm a crazy guy. So that's our whole data set. We're going to use only the first 4 again to classify. We're not doing anything different from previous now. We just did the first clustering, the deep clustering here, and here we take the first and the third from the first cluster and just the first cluster from the deep one. I know I say the cluster word like a million times. Sorry if it's complicated. I'm gonna keep doing it. though. So I can plot now the data, and here, what did I plot it before? Okay, look how many the data was, and look how many the developers are. So all these points that we have now at the dev normalized dataset is only the developers from our dataset. Again, I'm going to eliminate all the missing values and count now the distance of the four metrics.